In the previous modules, we've been studying univariate data. In this module, we're going to look at two-dimensional data. As an illustration, we're going to look at heights for fathers and sons. So if we're asked to summarize these two-dimensional data, what will we do? Well, what we've learned is that we can use the mean, the average, and the standard deviation to summarize each. If we did that for this data set, we would miss out on a very important characteristic of the data that we can see by simply making a scatter plot. A scatter plot just shows the data in its two dimensions. So we have a series of points. Each point represents the height of a son and the height of the corresponding father. When we look at this plot, we immediately see that there's a trend that as the father height goes up, so does the son's. That very important characteristic of the data is not summarized by giving the averages and standard deviations of each of the two. That particular characteristic is best summarized by the correlation. To compute the correlation, we simply standardize the units and then multiply them together and take the mean of that. That's going to give us 0.5. Now, what is the interpretation of the correlation? What does it mean? When the data is normally distributed and is two-dimensional, the correlation adds the extra information we need so that we can describe the proportion of data in any given two-dimensional interval. And it also helps us make predictions. So I'm going to illustrate the use of correlation when we make predictions. So suppose that you're asked to predict the height of a person who has been randomly selected from among the sons. Because the data is normally distributed, you know that the average is the best guess. That's the place that maximizes the distribution. That's the place where you have more people than any other height. Now, if I change the problem and I tell you that I know the father's height and I know that it's 72, how does that change the prediction for the son that is known to have a father who's 72 inches? We wouldn't predict the average anymore because we know this son has a taller than average father, and therefore we expect the son to also be taller than average. So what is the actual prediction? We can actually do that we can actually get an idea of what it should be by stratifying the data, and we're going to notice a pattern. So stratifying data is also a very powerful approach to exploratory data analysis, so I'm going to show you what that means. So I have the data Y, and now I'm going to stratify by father's height. So I'm going to create groups by having father heights in common. So we're going to round the father's height to the closest inch, and then we're going to group the son's heights by that value. So let's show you how you do that with the function split. You can see it has created several groups. So these are the heights of the sons that have fathers who are 72 inches. So we can plot these with box plots. So for every group you have several numbers, you can make box plots, and now look, we can see that there's definitely a trend. And we also notice that the trend does look like it's linear. For the particular question we asked of the 72-inch height father, what's the prediction for that son? We can just take that average of that group, it's this group here, and that average is 70.67. Now, we did see that it's a linear relationship. For normal data, it actually is a linear relationship, and this is what's going to help us interpret what this correlation means. So let's standardize the data. Just to make this a little simpler, we're going to standardize the both father and son's heights so they're in standard units. Now we're going to make a plot showing you the mean of each one of these strata. So we're going to apply this function tapply. We're going to use it to compute the mean of each group determined by rounding the heights, now in standard units, but but now we're going to do it to the closest quarter. So we have, let's show what these means are. So we have these means for each of these groups. So for all the fathers who were 1.75 standard units away from the mean, the average height of those sons was this much, negative 0.75. So we can plot that. We need to extract the father heights, which are actually in the names of this vector. See, so we're going to use the names of that vector here. Those are the names. That's what that function does. And we're going to turn those into numbers. These are characters. So we turn them into numbers. Now we have the father heights, and we can make this plot. So you can see that it does appear to be linear. All we need now to make predictions is the slope of that line, which turns out to be the correlation. So that's the interpretation of the correlation. If you have two data sets that are normally distributed and they have some correlation, if you turn them into standard units, then the correlation is the slope of the line that you would use to predict variable y given variable x. So these 5 numbers, the means, the two standard deviations, and the correlation, are a very good summary for data that is two-dimensional and normally distributed. Now, just like we need to be careful with non-normal data when we use these summaries, the same is true for the correlation. I'm going to show you a very quick illustration. I'm going to generate some data that's uncorrelated, but then we're going to make a mistake and change the first value to a very large number for both lists. And when we do that, we make a plot. You can see the data is uncorrelated, and then there's that point out there. That point makes the correlation very high all of a sudden. So as we described in one of the modules, we can use Spearman correlation to obtain a robust estimate of the correlation in this case, and it would be much better. This one is 0.12. This is much closer to 0, what we think should be the right answer, than when we just take the straight correlation, also known as Pearson's correlation.